So I'm Cristina, and this is a joint work with Veronika Thost. So just to give you an overview of like the motivation about this work is that, as we all know, logical rules are a useful and a compact way to represent knowledge. So over the years, many ILP methods have been developed, and more recently, also they got the attention of the machine learning community. So we start to see a lot of neural ILP systems. So the problem with neural ILP systems is that they don't have appropriate data sets. So we can see that we only find very simple data set, so toy problems with very simple rules. And also the evaluation methods are usually very machine learning oriented and often are not suitable for this logic context. So what we propose is a tool that is composed of two parts. So the first part is a generator. So we can generate synthetic data set of different types. And the second part is an evaluator that has different evaluation metrics, both machine learning inspired, but also logic inspired. And moreover, we provide, along with our tool, sample data set that we pre-generated. So now we are able to test ILP or neural ILP methods more extensively. So, as I said, the main feature of this of our tool is that it is highly parameterizable. So we can decide many things when we want to generate a data set. For example, how many predicates we want, how many constants, the number of facts, so the size of the data set, the arity of the predicates, the length of the rule, and so on. Also, like the level of completeness, so how many consequences of the rules are present in the data set, the amount of noise, like how many wrong facts we inject in the data set, and how many support facts are we removing. So we have different evaluation metrics, and one of the important features is the type of dependencies between rules. So we identified 3 different types of rule dependencies, plus a mixed type. This is just a mix of the previous 3. And just to explain you a little bit what we mean with dependency between rules, we can look at this graphical representation on the bottom of the slide, where these graphs, so each node in this graph represents a logical rule. And there is an edge between 2 nodes only if one body atom of one rule is the head of another rule. So here we can see the predicate P6 is in the body of the first rule, and here is the head in the head. So we can define different types of these graphs. For example, the type chain only allow one outgoing edge from each node, while the RDG type allowed multiple edges, and the RDG allowed also the special nodes, the disjunction nodes, that allowed the instantiation of one body atom of one rule in different ways. So there is a disjunction. So here we see an example on the left of a data set, very small example of a data set that can be produced by our system. And we can see that all the predicates and the constants are not interpretable. This is because it's a synthetic data set. Okay, so now that we generated our data set, we want to evaluate like the results of our ILP or neural ILP methods that was run on this data set. So we start with the original ground truth logical program, so a set of rules, and the induced one. So we implemented in our tool some of these standard machine learning metrics like accuracy, precision, recall, F1 score, of course, interpreted in our logic scenario, but also some logic inspired metrics based on the Herbrand distance, so the distance between the minimal Herbrand models defined by the 2 logic programs. But the problem of all these metrics is that they require to materialize the whole programs, so to grant the programs, and this could be very computationally inefficient. So we also define another evaluation metric called rule score. So this one only look at the rules in the two sets. So as you can understand, this is very efficient since we don't have to grant the whole program. Okay, so then we perform some experiments. So the goal of our experiments is to demonstrate that we need tool such ours, because we need to have a diversified portfolio of data set to evaluate ILP and neural ILP systems. So to do this, we consider 4 different ILP methods. So the first one, FOIL, is a traditional ILP system. Then EMI Plus is a non-neural rule mining system, while the last 2 are 2 neural approaches. So, and we evaluated on this sample data set that we pre-generated from our tool. This one has around 200 data sets. And then we also compared on this small, complete data set that is often used in neural ILP papers. And this one just defined the concept of even number given the predicate about the successor. Okay, so the first results is that we want to check how these ILP methods perform on different factors. So the first one is missing information and noise. So we can see that, for example, if we consider FOIL, we can see that it's not robust to incompleteness and noise, because we can see a huge drop in performance once we start to add incompleteness, and even more when we start to add noise as well. While we can see that these last 3 methods, the QNeural and EMI Plus, they don't have this drop in performance, so we can see that they are robust to incompleteness and noise. So the third result is like we want to see how the rule structure impacts the learning. So, and here we started with the simple one, so the chain dependency between the rules, and then we introduced the RDG and DRDG. So, and here we can see that, for example, FOIL has a drop in performance when we increase the complexity of the rule, but this is true for all the methods, because all of them, they have a drop in performance going to a more complicated rule set. So, and the last one is the scalability. Also here, we want to test how the scalability impacts the different ILP methods, and we do this in 2 dimensions. So the first one is starting from a small data set of size S, going to a bigger data set of size M. And the second dimension is this number that you can see here, 2 and 3, and this is the depth of the rule dependency tree. So we can see that, for example, FOIL does not have much drop in performance going from a dependency depth 2 to a dependency 3, while it has a huge drop in performance going from a dataset of type S to a bigger dataset. So we can see that FOIL is scalable only on the rule depth, but not on the dataset size. And similar observation we can do for the other system. So for example, neural ILP, this one is scalable only for, so is scalable on the dataset size, but not on the depth of the dependency tree. Okay, so the second result is we want to understand how these evaluation metrics perform. So we consider all of them, and we noticed that some of them, like the accuracy and age accuracy, are not suitable for a logic domain because they always provide a very good performance. This is why they consider also true negative example as part of the correct predictions. So then we can see only this second part of the evaluator metric is suitable for this logic scenario. And finally, the last result is that we want to see how this R score that does not consider the facts in the dataset and the constants, but only consider the rules that are induced. And we can see that this behave very well and is very similar to the F1 score and the H score. And this is, but it has the advantage of this computational efficiency because it does not require to run the whole program. So, and this concludes my talk. And I just want to point out that the tool is available on GitHub and is open source. So please try it. And since it's open source, you can even improve it and contribute to it. Thank you.
Okay.